Have you ever wondered how cutting-edge technology can transform an ordinary hydraulic manifold into a marvel of engineering? Today, we're diving deep into the world of metal additive manufacturing, where innovation meets aviation. Welcome to the Metal Additive Manufacturing channel, your go-to source for metal additive manufacturing technologies and their game-changing applications. In this video, we're showcasing a groundbreaking case study on optimizing part performance by redesigning a conventional hydraulic manifold for aircraft landing gears. Our journey will take us through a detailed workflow that not only achieves significant weight reduction, but also meets the rigorous standards required for aeronautical components. Additive manufacturing is revolutionizing the way we create metal components. Unlike traditional subtractive methods, additive manufacturing builds parts layer by layer, offering unparalleled design freedom and material efficiency. In this video, we'll be focusing on selective laser melting technology. The purpose of this case study is to redesign a conventional hydraulic manifold used in aircraft landing gears. The goal is to leverage additive manufacturing technology to create a lighter, more compact manifold that meets stringent aerospace standards and that can be retrofitted. This case study will cover the entire redesign workflow and the considerations involved in designing for metal laser-based powder bed fusion technology. The original manifold was designed for conventional manufacturing methods, utilizing a stainless steel or aluminium alloy billet. It featured internal pathways for fluid flow created through drilling processes with specialized tooling. The design was functional, but had limitations due to the constraints of traditional manufacturing techniques. The primary challenge was the complexity and cost of the manufacturing process, which involved multiple steps such as machining, trimming, and drilling. The design left little room for optimization, leading to potential material waste and a heavier end product. The technology used to manufacture the new design is known as Selective Laser Melting, or SLM. This innovative process involves fusing metallic powders layer by layer using a high-powered laser beam. The result is a solid, three-dimensional object meticulously crafted from a digital model. SLM stands out for its ability to produce complex geometries with precision, which traditional manufacturing methods may find challenging. Now, SLM offers remarkable advantages for manifold production. Firstly, it allows for significant weight reduction, which is crucial in aerospace applications. The design freedom afforded by SLM enables the creation of intricate internal channels that optimize fluid dynamics, leading to enhanced performance. Additionally, the layer-by-layer approach minimizes material waste, aligning with sustainable manufacturing practices. Lastly, SLM can shorten lead times, accelerating the transition from design to production. Let's dive into the core principles of design for additive manufacturing, or DFAM. DFAM is a design approach that leverages the unique capabilities of each additive manufacturing technology. Unlike traditional manufacturing, additive manufacturing typically allows for complex geometries, material savings, and functional integration. Turning to our case study, these DFAM principles are tuned to selective laser melting attributes and guide the redesign of a conventional hydraulic manifold for aircraft landing gears. The original manifold, machined from a solid block, is reimagined for selective laser melting. This is achieved by re-engineering the internal flow channels, eliminating unnecessary material, and integrating multiple parts into a single, cohesive unit. The redesign process was initiated by analyzing the conventional manifold and identifying areas for improvement. Our goal was to optimize the manifold for metal SLM technology, focusing on weight reduction and enhanced fluid dynamics. The redesign involved an iterative process where we utilized CAD software to modify the manifold's internal ducts, ensuring they were self-supporting and free of sharp angles that could initiate cracks. Computational fluid dynamics, CFD, simulations were also employed to evaluate the hydraulic performance of these channels, aiming for smooth flow transitions and reduced pressure drops. The structural simulations were conducted using finite element analysis, FEA, in a dedicated simulation environment. This helped identify stress distributions and optimize the design to withstand the required load conditions. In the prototyping phase, selective laser melting was used to rapidly create a tangible model of the novel hydraulic manifold, rapidly building a prototype that closely represents the final product, helps engineers to evaluate its design and functionality in a real-world setting. Following the production of the prototype, a series of rigorous tests, like proof pressure or vibrations testing, is carried out to assess the manifold's performance. These tests are crucial in demonstrating the manifold's compliance with airworthiness certification requirements and its readiness for aerospace applications. The redesigned manifold achieved a 40% weight reduction compared to the original, without compromising on structural integrity or flow performance. The AM-driven design process significantly reduced the number of manufacturing steps, leading to lower production costs and shorter lead times. The elimination of complex tooling and the ability to produce closer to the point of use also contributed to these savings. Overall, it was shown that the new design enhances the economic viability of the component in the long term. One of the significant challenges faced in the redesign process was optimizing the internal flow channels for the manifold. The goal was to minimize tensile stress due to cyclic pressure loads. Another challenge was ensuring the structural integrity of the manifold under various load conditions, such as proof pressure, burst pressure, and impulse pressure. This demanded rigorous testing and validation against aerospace standards. A key takeaway from this project is the importance of an iterative analysis process. By continuously refining the design and smoothing out structural criticalities, we achieved a manifold that was 40% lighter than the initial CNC machined solution. Incorporating accelerated testing that closely replicates operative conditions is also crucial for assessing failure modes and effects and fine-tuning the models. In this video, we've explored the comprehensive workflow used to redesign a hydraulic manifold for aircraft landing gears using metal additive manufacturing technology. We began with the initial design constraints and progressed through design optimization, structural simulations, and practical testing. Looking ahead, the success of this manifold redesign opens the door to reimagining more components with complex geometries and customized features. As the industry continues to refine additive manufacturing processes and materials, we anticipate significant advancements in performance, efficiency, and sustainability within the aerospace industry. Thank you for joining us today. Don't forget to subscribe and check out our website,